Today we are going to begin the last portion of our trig unit. So far in trig, we talked about right triangle trig and we did SOHCAHTOA. That's going to come back again. We talked about our 30, 60, 90, and 45, 45, 90 triangles in unit circle. That's going to come back again. Okay? Those are things that we talked about in the first portion of our trig unit that are going to come back again in this last one and be important to us once again. We also talked about law of sines and law of cosines. We're done with those. Those aren't going to come back, but just to kind of review what we've learned about trig. And then we just finished up learning how to do sine, cosine, and tangent graphs. Okay? But in this last portion of our trig unit, those first things that we studied, SOHCAHTOA, 30, 60, 90, 45, 45, 90 unit circle, are going to be important to us once again. In this last portion, we're going to be looking at something called identities and equations. This first type of problem is very similar to something we've actually studied before. It asks us to give 5 trig functions as answers given one trig function already. Okay? This particular one gives sine, but it could give us any of the 6 trig functions. So we're going to do this by graphing and by SOHCAHTOA. So to graph this, the first thing it tells us about our angle is that it should be between pi halves and pi. So if we're going to graph our angle, where is that going to be? Where were pi halves and pi? What angle is pi halves? 90. And what angle is pi? 180. So our angle is going to be somewhere in between here. We're just going to draw it. Doesn't matter where, just somewhere in between there. Our picture doesn't have to be to scale. So somewhere in between 90 and 180, we're going to put our angle. Then we learned we always connect with our x-axis to make a triangle. We learned our angle is always next to the origin. And the trig function that's given to us gives us 2 sides of this triangle. We are given the sine of this angle. According to SOHCAHTOA, what does sine tell us? Opposite over hypotenuse. So that tells us that we have an opposite of 3 and a hypotenuse of 5. So we can find the third side of the triangle using Pythagorean theorem, or this is actually a special triangle, so you might know it without the Pythagorean theorem. But 3 squared plus x squared equals 5 squared is our Pythagorean theorem for it. Remember, the hypotenuse always has to be by itself. So we get 9 plus x squared is 25, 16, and we get 4, kind of. What do we really get? Negative 4. Remember, on our graph, we need to consider direction, and this is in the left-hand direction, so that needs to be a negative 4. Once our triangle is labeled, then we can answer the question. It asks us to find the other 5 trig functions. So we don't need to find sine because they already told us sine, but we need to find cosine, tangent, cosecant, secant, and cotangent. So cosine, using SOHCAHTOA, cosine would be adjacent over hypotenuse, so negative 4 over 5. Tangent, opposite over adjacent, so 3 over negative 4. And the other 3 are reciprocals of the first 3. So cosecant flips over sine, which is the one we were actually given. Secant flips over cosine, and cotangent flips over tangent. Questions? So first you're going to use that inequality to choose which quadrant to place your triangle. Okay? So remember, our key angles around 90, 180, 270, and 360 are 0. Okay? So it's going to give you a quadrant to place your angle in, connect to your x-axis. That's important. Always go to the x-axis and then use the given one to label 2 sides. This one gave us sine, but it could give you any of the 6 trig functions. So use that SOHCAHTOA to label two sides, Pythagorean theorem, find the other one, and then you can find the 5 missing.
Can you go over making the triangle with the inequality?
Yep, so what we're going to do is take that inequality of pi halves and pi, and back in the first portion of our trig unit, we learned that pi is equal to 180, that pi radians is 180 degrees, and so if we have pi over 2, that's the same thing as 90, and pi is just 180, so that tells us which quadrant to place the angle, that we want to place it between the 90 and the 180 mark. So the other one around the bottom in radians would be 3 pi over 2. That would be our 270. All right, go ahead and give this one a try. Okay, first thing we want to do is select our quadrant. So we're told that it's between pi and 3 pi over 2, or that would be between 180 and 270. It's going to be somewhere down in here. And we connect to the x-axis always. Theta goes next to the origin. And we are told our cosine, which is adjacent over hypotenuse, is 5 and 13. So 5 for the adjacent, 13 for the hypotenuse. One of those needs to be negative, so that we would get a negative 5/13, and we learned our hypotenuse is always positive, so that 5 must be the negative. Then to find the third side of this triangle, this is kind of a special one, so you might just know it, otherwise we Pythagorean theorem. 13 is the hypotenuse, so that has to be alone. Negative 5 squared plus x squared. Remember that squaring a negative gives a positive value. So that becomes a positive 25. And subtracting that out, we get 144. Square root of that is 12. But direction-wise, that 12 is going downwards, so it's a negative 12. Once the triangle is labeled out, we can find the missing trig function. So we need sine. We don't need cosine because they gave it to us. We need tangent, cosecant, secant, and cotangent. Sine is opposite over hypotenuse. Tangent is opposite over adjacent, and we can cancel those double negatives. Cosecant flips over sine. Secant flips over cosine. And cotangent flips over tangent. Questions? The night 1 portion of the assignment, so the part that will be assigned for tonight, due the next time that I see you, is just this type of problem. We're not going to stop here. We're going to do some more examples of the next type of problem, but the homework assignment for tonight is just this type of problem. But in both of these, our third side of the triangle ended up very nicely. Right? That will not be the case on all of your problems. So let's remind ourselves how to deal with that. Let's say, for example, I had a problem that has something like, no, I don't like that. This. Okay, so I find my quadrant. In this one, it would be between 0 and 90 would have been our quadrant guideline. In this one, I would have been given that sine is equal to 1/3. Opposite and hypotenuse 1/3. Okay. Now when I go to find my missing side here, this is not going to be a nice triangle. So we will use our Pythagorean theorem. 3 squared equals 1 squared plus x squared. So I get 9 equals 1 plus x squared. 8 equals x squared. And take a square root. No decimals, simplified square roots. So what's a perfect square that goes into 8? 4. So this is square root of 4 and square root of 2.
This is Sarah. Can you send Josh Combs to the office?
Yep.
Thank you.
So our third side of the triangle on this problem is 2 square root of 2. Okay. Then when you go to do your SOHCAHTOA fractions or the reciprocals, remember that you are allowed to leave square roots in the bottom of the fraction. The book won't. So if you check your answers in the back, they will not have done that. But you may leave your square roots on the bottom, but I don't want decimals. I want them as simplified square roots. Okay? So just like we did it before, but it's been a little while since we've done this type of question. Simplified square roots, no decimals, but you can leave them on the bottom. The next kind of problem we're going to look at is going to use some identities. They look intimidating. They look even worse here because PowerPoint hates it when I use parentheses inside of formulas. But they are on your paper. You do not need to memorize any of these formulas. Okay? When it comes to the test, I have a formula sheet that I will give you. It has these ones that we're looking at today, but then there are going to be more throughout the rest of this unit we're going to look at as well, and you don't need to memorize any of them. We just need to know how to use them, and so that is our next type of problem. These are some strategies. These are not printed on your notes, so you might want to write them on your notes. The first strategy that we do when we're trying to simplify a trig expression, which is the next type of problem we're going to look at, is simplifying. The first thing that we're going to try to do is factor it. I said here that it's rare, okay, so don't expect to do this in every single problem, but if it's possible to do it, it can be very helpful. So we're going to look for factoring. The next thing we're going to do is check that identity list. So that's printed at the top of your sheet here, or the one that was just on the last slide with our identities. And we're going to look to see if we could make any substitutions or swap out a part of the problem. Our third strategy is that we're going to change everything into being in terms of sines and cosines. All 6 trig functions could be written as either sine or cosine or both. So to limit the number of trig functions in the problem, sometimes we're going to change everything into sines and cosines. Those are our 3 main strategies, but it's not like step 1, check, step 2, check, step 3, check, and you're done. Sometimes you might need to, after you, for example, change things into sines and cosines, then go back and check your identity list again, because maybe now there's something that could be substituted that couldn't before. So we kind of repeat through this list until we're done. One of the hardest parts of simplifying for students is knowing when you're done. Like, when is it good enough? When is it simplified enough? A good rule of thumb is, if it is down to having just 1 trig function represented in the problem, it's probably good enough. Okay? So if we can get it down to just having 1 trig function in there, and if it's down to just having 1 term, if it's just 1 thing, there's no additions or subtractions or anything else with it, then it's probably good enough too. So our first strategy said factor. We're not going to do that every time, but when we can do it, we want to try to do that. When we factor, we're looking for something in common to both terms. So what do both of these terms have? A secant. So we are going to take a secant outside, which leaves a tangent squared theta plus 1. Because remember, if we distribute back through, we need to end up with what we started with. So a lot of students forget that plus 1 because they're like, oh, well, it just all went away. But then that would be changing the problem. We always want to think about, if I redistribute this thing back out, do I get what I started with? Okay? Because we're not changing the problem, we're just changing the way it looks. Our second strategy was to check the identity list for anything that matches where we could make a substitution. The first group of identities on your sheet are called the Pythagorean identities. They are called that because they actually come from the Pythagorean theorem, so there are a lot of squared things in them and a lot of 1s in them. One of those Pythagorean identities says that secant squared of theta is equal to 1 plus tangent squared of theta. It's the second one on the list. The reason why I'm choosing to look at that one is because it looks a whole lot like my problem. So in here I have a 1 plus tangent squared, and here I have a 1 plus tangent squared. Because remember, adding 1 plus 2 is 2 plus 1. It doesn't matter what order those are coming in. So those two things that are circled are exactly the same. What that means is I can take this thing it's equal to and plug it right in and substitute or switch it out. So I'm going to rewrite this now as that secant of theta that was out front, but instead of tangent squared plus 1, the secant squared of theta that it's equal to. Okay, so I'm making a swap. Since 1 plus tangent squared is equal to secant squared, I'm swapping it out.
How do you get the secant squared equals?
That's on your identity list. So that's on that formula sheet, it's the second one down. I chose that one because it looks a lot like my problem. So that's why I picked that one from the list, but that's on your list. Now at this point I have a secant times a secant squared. Well, what would x times x squared be? X to the third, or x cubed. So what would a secant times a secant squared be? Secant cubed. And that is done. Again, I said a good rule of thumb for knowing when you're finished is if you can get it down to just one single term, then that's going to be good to go. Sometimes we won't always be able to get it down to just one single term, but if you can get it down to just one thing, it's done.
So what happens to the tangent squared theta this one?
It became the secant squared because that identity tells us that 1 plus tangent squared of theta is exactly equal to a secant squared. So we're swapping it out. These problems are very uncomfortable in the beginning. We hope they get more comfortable as we go, but they are tricky to see where we're going with these. So please, please, please feel free to ask lots of questions. Our first strategy is to factor when we can. So in this problem, do both terms have something in common? Cosine. So we're going to take out that cosine of theta, and we're going to be left with then 1 minus sine squared of theta. And if we would distribute back, we would end up exactly where we started. We don't want to do that because then we're going around in circles, but it's a good idea to just quickly double check and make sure that that happens so that we know we haven't actually changed the problem, just changed the way it looks. Our second strategy is to look for substitutions. So again, that first group has a lot of squareds and ones in it. So when I have squared things and ones in it, that's where I look for substitutions. In that list, one of them says, right, exactly like here's here, sine squared of theta plus cosine squared of theta equals 1. That does not exactly match our problem, but it has a whole lot of the same stuff as our problem does. Okay, our problem has cosines and ones and sines in it. This has cosines and ones and sines in it, so it's looking a whole lot like our problem. But there's nothing like the last one that's exactly the same. What I'm going to do here is say that sine squared plus cosine squared equals 1. So I'm going to take that 1 and I'm going to replace it with a sine squared plus cosine squared. Now this feels a little bit counterintuitive because our goal is to try to simplify, which means to make smaller. And by doing this, I'm actually making the problem bigger and messier for a minute, but sometimes that has to happen. Like I think about, okay, it's almost spring cleaning time. I do believe spring will come eventually, and then it will be spring cleaning time. And every spring, I go through my closet to clean out and get rid of the stuff I don't wear anymore. I take everything out of my closet and throw it on my bed. So my room gets really messy for a little while, but then through the cleaning process it gets better. Okay? So sometimes you have to make things a little bit messier in the process to actually turn out better in the end. So we're going to take that 1 and we are going to replace that 1 with a sine squared theta plus cosine squared theta. Why would that be helpful now? Because it cancels out the sine squared that's there. Sine squared minus sine squared is 0, so those cancel each other out, and they are now gone, so I'm left with cosine of theta times cosine squared of theta, which I can multiply together and get cosine cubed of theta. Okay, so our strategies, we factored, we looked for a substitution. There wasn't necessarily a nice and clean substitution to make, but there was a substitution that used a lot of the same stuff as our problem. So that's how we picked that one. And then we went through and did some algebra to simplify. Factoring is a rare strategy. Factoring can only be done when we are adding or subtracting terms that have the same stuff in it. In this one, we really just have a multiplication. So we're not going to be able to factor in this one. So that means our very first strategy then, since we can't factor, we jump down to the next thing on the list, which is look for substitutions. So I see that pi halves minus x is kind of the messiest part of this problem. So the second group of identities on your sheet are called the co-function identities. And those all have pi halves minus theta on your formula sheet, but theta and x mean the same thing. So don't worry about whether it's a theta or an x. They use the same formulas. And I'm going to look for the one that uses cosine, since this problem says cosine. And I see on there that it says cosine of pi halves minus theta equals sine of theta. Okay, so that's in that second group of identities on your sheet, and it's actually the second one down in that group. This problem uses x's, so I'm just going to use x's instead of thetas. They don't matter, you can swap them out. Doesn't matter what variable we use, as long as we're consistent. So now since this cosine stuff is equal to sine of x, I'm going to just plug a sine of x right in for it and swap it out. And I'm not going to do anything with that second part. Now our third strategy that we haven't used yet is to write everything in terms of sines and cosines. All 6 trig functions can be written as sines or cosines. So to do that, sine is sine. It's fine. We don't need to make any change to that. I like to write it over 1 just because we're going to end up with a lot of fractions, so I'm going to make everything into a fraction. Cotangent. All right, well, cotangent is one of our reciprocal functions, but back a long time ago in chapter 13, we talked about what tangent was. What is tangent? Sine over cosine. When we were learning our unit circle, we learned that tangent is equal to sine over cosine. So this problem says cotangent, which is the reciprocal. So cotangent would be equal to cosine over sine. Making those substitutions, your sine and cosine substitutions, is something that you need to be able to do in terms of knowing that tangent is sine over cosine. That's not printed on your identity list on your sheet because that's chapter 13 stuff that we already talked about with our unit circle. So that's stuff that you are expected to be able to remember and do. These other identities that are printed on there, those will be given to you on a formula sheet. But cotangent is equal to cosine over sine. How does that help us? What can we do now? We can cancel out the signs. And we are left with then just a cosine x. We're going to do one more example today. So first strategy is factor. There's nothing in here that matches in common to everything to be able to pull it out, so we can't do any factoring. And again, that one's pretty rare. You're not going to do it every time, but when you can do it, it is often very helpful. So then we're going to look for substitutions. So on the substitution sheet, I'm thinking about these pi halves stuff. So I'm going to look at the sign of pi halves minus x and look up on my sheet what that is, and it says it is cosine of x. That's the first one in the second group of identities there. So I'm going to take that sign of pi halves minus x, and I'm going to plug in a cosine of x instead. I'm not going to do anything with the rest of the problem right now. With having a negative by the x, the third group of identities on your sheet says negative angle identities. But there is not one that says secant. It's only the big three, sine, cosine, and tangent. So there's no substitution we can make for that bottom part right now. So our third strategy was to change everything in terms of sines and cosines. So I'm going to have 1 say 1. I'm going to write cosine as cosine over 1, just because I like to turn everything into a fraction. And secant is the reciprocal of which one? Cosine. So we're going to write it as 1 over cosine of negative x. Since it was a negative x, it's still going to be a negative x. But secant is the reciprocal of cosine, or secant is 1 over cosine. So I'm rewriting the bottom part of that fraction as 1 over cosine. How do I divide by a fraction? Multiply by the reciprocal. So instead of dividing by this fraction, I'm going to multiply by the reciprocal of it. And that gives me 1 plus cosine of x times cosine of negative x. Now if I check out that cosine of negative x identity on the sheet, it says that cosine of negative x is equal to just a cosine of x. That's under the negative angle identities on your formula sheet. So I'm going to take this cosine of negative x, and I'm going to switch it out for just a regular cosine of x. So if I switch that to just a regular cosine of x, then what do I have? Cosine squared of x. Now I see squareds and I see ones, and that makes me think about that first group of identities. In that first group of identities, there is one that says sine squared x plus cosine squared x equals 1. If I do a substitution here, I would change that 1 out for a sine squared plus cosine squared. Will doing that help anything go away? So if I change this 1 out to a sine squared plus cosine squared, which I can do, does anything cancel? Everything's added, right? So we did that once before, but we had something subtracted, so they cancel each other out. But here, everything is being added. So doing that doesn't actually get rid of anything. Now it's just bringing in more trig stuff. So we don't want to do that. And our final answer is 1 plus cosine squared. So it is not always possible to get your answer down to just one single term. If you can, you know you're done, but sometimes 2 terms is as good as we can get it. Tomorrow we're going to be working with these same formulas some more to do something called verifying. But tonight's assignment is the night 1 portion of the homework that's printed at the bottom of the back of that page. And it is just the first type of problem that we looked at. There aren't any of these simplifying problems in there yet. They will be in the night 2 portion.